All right, thank you, Carl. Appreciate it. Okay, so let's get started. We're a couple minutes after 6 o'clock. So we'll get started. Doesn't look like we have anybody waiting to join us in the room. That's good. All right, so welcome everybody to the final meeting of the Seattle Rust user group in 2025. This is, been a very good year. So we're here at Bellevue City Hall, and we operate under 2 codes of conduct. And basically, it's treat everybody with dignity and respect. If you find that somebody is not treating you with dignity and respect, please let them know. And if the behavior persists, then please let me know, and I will do what I can to assist. As always, the slides for this can be found at slides.com, U007D, which is my online technical alias. You can find this month as well as any other month that we've done since we rebooted the group almost a couple years ago now. So how many people here are new to this group? Anyone? No one's new? Oh, one. Okay, we've got one new person. Welcome. All right. So generally what we like to do is some introductions, just to, be around the room. You're going to hear me blab on a lot, and so get to know different folks. Since most of us are, have been here before, what I would like to do is have people talk about an interesting project that they've heard of, or they're working on, or would be interested in working on, just something that is, piques your fancy. And so this way, folks get an understanding of the interest of some of the other folks in the room. So I think most folks here know about one of my other interests is building electric cars. So I'm building an electric car project, of course using Rust for that from scratch. And that's a very time-consuming project, but it's a lot of fun. I actually did a talk on it at the Seattle RustConf this past September. So if you are interested in learning more about that, let me know, and I'm happy to point you to the YouTube talk where that's now recorded. You can check it out if you're interested. Hello. Okay. Is there anyone else who'd like to talk about an interesting project that they worked on, heard about, or curious about? Okay, Jeff.
Thanks, Ryan. I'm Jack. I definitely met almost everybody in the room. Did anyone else read this blog post, just sort of a blog post called Future Lock from Oxide Computer Company? So that made a splash in the subreddit and stuff. I think one of the most interesting parts about that blog post was the part near the end where they said it's hard to tell what about this code was wrong. Like there's like no specific mistake, it's just the end result of deadlock. That totally nerd-stunned me. I've been trying to figure out how to write down a rule about what was wrong, and I think once you write down that rule, you want to design some new async primitives that don't break that rule. So I've been thinking about that. If anybody else wants to talk about async, what makes it correct, find me after.
There's a guy that I referenced in my talk who extended the Rust language to be fearless deadlocking. Right? We have fearless memory safety. We have fearless concurrency. And he extended Rust to be fearless deadlocking. It will not deadlock.
Like in a multi-threaded.
In a concurrent environment. And it's a compile time error if you do it wrong. You might be interested in that. Let me know. I will get you the link to his talk. It's at the Montreal 2024 RustConf talk. It was excellent. But it's about taking what Rust promises and actually lifting it even higher than what it gives. And so I'm trying to do the whole car project as type stated through hardware, through all kinds of stuff in that similar vein. So he calls it X safety, where X is whatever you need: memory safety, concurrency safety, deadlock safety, hardware safety. But to get those types of fearless Rust promises across all new domains that the language didn't ship with is apparently, well, he shipped code to do it. So, and as you probably know, embedded HAL provides type safety on hardware. So there's 2 domains that Rust can provide that same safety guarantee, a fearlessness that it didn't ship with out of the box. That might be of interest to you.
Would you mind throwing that in the Discord?
Yeah, absolutely.
I missed that talk. I was at a different one.
Yeah, okay, no problem.
So, like a year ago, we did a thing with our Raspberry Picos and learned how to get them to use Rust, and talked a little bit about using Embassy and async to make it more reasonable. And Brett and I co-authored a blog post that talked about that. It hasn't had as much impact as I wanted it to have.
Uh-oh. We'll fix that.
So the first thing I did is I bought like a $90 part set from Sunfounder on Amazon with all these little $1 and $2 parts. And now I'm just going through and making sure that you really can program all these, like an RFID badge reader, and not just running 2 sets of smart LED lights, but multiple streams of lights, all at the same time, and a distance sensor, and all that. So that's turning into a medium-sized project, because I want, the whole point is to show that you have a nice API here, that it actually looks nice, not just that you got everything running at all. Because
Exactly.
we could get everything running at all, probably with MicroPython. We want to do better than that, and then figure out a way to have some impact. My impression now is people are using Rust unembedded without a real-time operating system, but they're often not using Embassy. They're just doing like really primitive
Using
stuff,
it like C.
looping. And Rust now has official support on STM, alternative to Pico, and the Raspberry Pi family. And I did get a little bit of that. I bought one, another $5 or $6, and I kind of got that working for the simplest thing, but not with Wi-Fi, because even though it's famous for having Wi-Fi and Bluetooth, the Rust drivers for that aren't ready yet. How can we move forward? My dream would be to have a booth at one of the maker fairs, like open source, where we'd say, come on up, let us tell you how to program your embedded in something way better, way faster than what you're doing with Python, and way better than what you're doing, and safer than what you're doing in C.
Pound define.
But
Yeah.
right now, I don't know that I could honestly do that.
Yeah.
It would be a learning experience to do that, because they would show, oh, here's the chip I need to use, and I'd say, oh, sorry, we don't have any support for that right now.
Yeah. If you look at there's a resource out there that tracks, because ST Microelectronics, STM, as you just talked about, has support. Obviously, Raspberry Pi Foundation has support. The Espressive, which is a Chinese low-cost manufacturer. There's a lot of Rust support, right, in terms of the ecosystem and the hardware built in for that. And there's a couple of other chips, the NXP. Yeah, there's a support for the NXP line, which are kind of a high-end, series of chips. They put out some really impressive boards, but you have a project in mind when you're
I want to use Embassy to make all the coding really nice.
Yeah.
And I'm not sure they're all there yet.
I think they're there on those particular platforms, because you have HALS for like all of those ecosystems that I just talked about.
We should
Obviously,
see
it depends on
the Wi-Fi or
board.
Bluetooth working on people get the STM or ESP, whichever one I meant to say,
Right.
because it has Bluetooth and Wi-Fi built in.
Right.
I don't know that the Rust supports those, because those are little processors within the little processor.
Yep. So it depends, again, it depends on the board, right? So I'm talking about instruction set architecture, and so depending on the board that you pick, you'll get really good support. If you get maybe a newer board or something that has not a peripheral on die, but say the Wi-Fi chip, which is another Cortex M0 on the Raspberry Pis, you can end up with, support issues.
I guess a closely related topic. A couple months ago, I finished a project of using a Docker image to cross-compile Rust, because we had a service that was deployed on my friend's Raspberry Pi.
Mm-hmm.
I gave a talk for that earlier this month. I'm thinking of doing it as a Seattle Rust user group talk as well.
I think that would be terrific. Yeah, well, we're going to have a call for talks coming up not too long from now, so that would be great. Any other thoughts, projects? Can be hello world. It doesn't have to be an advanced topic. Anything anybody else want to mention?
In the vein of the motor
or the electric car, I love motor controllers and motor controls. So I keep working with people in C++ and C, and they keep saying that Rust is slower and worse than C and C++. So I figure I'm going to make a little motor controller on an SDM part, and I'm going to do it in Rust, and I'm going to do it in C++, and
It'll just work. Yeah. Nice.
So if any of these projects
Sound interesting, or you'd like to know more? We have a break between the talks. Make a note of the person who is speaking, and reach out, make a connection. That's why we're here. All right, upcoming meetups. As I mentioned earlier, this is our last meetup for 2025. We have, I think we're back to the third Thursday of every month. So Thursday, January 15th, February 19th, and then again on March 19th. As always, I'd love to thank the volunteers. We work really hard to try to keep everything as smooth as we can. And we also work hard to not work hard, right? We want to keep it to about an hour a month or so. So, thanks to everyone who helps put this together, from, assembling the speaker schedule, doing the AV, putting the postings up on meetup.com, doing the admin on the Discord server. There's 400 or 500 people now on the Discord server. So, and it's great. We don't have, behavioral issues or anything like that going on. So, people are really helpful. There's some mentorship channels, there's some help channels, and people seem to be getting help. And it's wonderful as we're creating a community where people can, interact and do stuff. So, as always, I'd like to give a round of applause to our volunteers for helping out. Thank you. As usual, and thanks to our C++ group for sort of modeling this behavior, but we're going to gather at Red Robin Overlake. This is not Red Robin Redmond Town Center. This is Red Robin Overlake. It's closer to here. And if you want to meet and grab some grub after the meeting, that's where many of us will be. All right. Like to, as always, I think we try to post our meetup recordings when we have them on YouTube. Also, I think recently you've been posting on Rust Videos, the official Rust Video channel. So those are great. As always, we would love to have speakers. For anybody who's been here for the last couple months, we've had 2 amazing talks from beginners the last 2 months in a row. So you don't have to be an expert at Rust or even computing to give a great talk. I think one of our best talks of the year was a beginner talk about, I don't even know what I'm doing, but here's what I did. And it was just fascinating. It was just fascinating, right? The fearlessness that was involved, both in doing the project in the first place and then coming up and presenting it as well. I was very impressed. So, I don't know, Ben, do you want to mention anything in terms of speakers? Oh, let me give you a mic, sorry. Yeah, come on up.
I'm volunteering you to give a talk in January, so you're going to get signed up, whether you like it or not, unless you really don't want to. Basically everything Brad said, we're always looking for speakers. I don't think I've ever said no to anybody, so as long as it's about Rust, we probably want it. Usually we end up doing like 2 45-minute talks, but we're definitely open to other formats too. Like if we want to do like a bunch of like lightning talks or something, that would be cool. Like maybe shorter 10-minute talks, and it's not so hard to prepare and everything. And then if people really like one, they could turn to a longer talk or something like that. I think that's about it really. Just if you have any idea, hit me up on Discord or just post in really any of the channels and I'll find you.
Cool. Thank you, Ben.
Yeah.
Yeah. We'll just hit the button. Oh, I figured it out. Thank you. Yeah, I think one of the key things is I've done a presentation a couple times, as a beginner, where I'm presenting a video that I saw that I thought was really interesting. So a lot of times, and that generated a lot of the first one in particular generated a lot of interactivity and conversation. So you might be learning something, and then you can come up here and show a 15-minute video and pause it and be like, what does this part mean? And have it in something interactive with the room going on. So you know, the sky's the limit in terms of the creativity of how you want to present. Don't let sort of the boring, slide presentation lecture format throw you off. We're open to any format you think might be interesting to you and to the folks in the room. So tonight, one other thing I wanted to ask here. Anybody have any news, any Rust news they want to share? Anything current events wise? New hardware support for Rust, anything like that? Any news? Bueller, anyone? Bueller?
New compiler was released today.
New compiler, 1.92, yes. So, anybody know what's new in 1.92? What's the headline new features in today's or yesterday's compiler release? That's not a rhetorical question. I didn't look at the release notes yet. I have it installed, but I haven't looked at the release notes yet. I just said yes.
This was a quiet one. I don't think there's anything like really
Nothing major? Okay.
Yeah.
Okay. I just always hoping for more const. So. All right. So the other thing is jobs. Anyone aware of any jobs, Rust related ideally? Just by show of hands, is anybody aware of any openings, job openings? Really? Well, we know, Oxide has advertised on our Discord that they have 16 positions open, so we know there's jobs. Everybody in the room should know that, right? Right? Yeah, there are jobs. So if anybody here is looking for a job that's related to Rust, come see me. I might be able to get you pointed in the right direction. As usual, most of the jobs are sort of intermediate level and up. If you're a beginner looking for a Rust job, that's going to be a little tougher. But it's still a conversation I want us to have on a regular basis because it's not a great economy, overall. I think Rust is doing better than the rest of the economy, but Rust is also very small still as a language. But if you're out there looking for employment, there are opportunities, and being what I do for the Rust group, I do get pinged on occasion. You guys, do you have anybody? Whatever, do you know anyone? So if you are looking for something, let me know, and we'll see if we can make a match.
There were 2 const stabilizations.
Well, there were 2 const stabilizations. What were they?
Slice, rotate left, and rotate right.
Really? That's actually interesting because, I'm actually using I'm using shift actually, not rotate, but I'm using shift right now for my car project. So that's actually really interesting. Thank you. That's great. Slice, rotate left, and slice. Slice, rotate left, and slice, rotate right.
Why would it be interesting for it to be const now?
Because I'm doing a conversion of an integer value into a fixed point value, roughly 10,000 times a second, and I'm counting clock cycles to get it down as efficient as possible. So the number of shifts that you're doing.
You're talking about bit shifts and bit rotates. He's talking about like array slices.
Yes.
Okay, so
That is correct. And so that's why I'm interested in that, because I can get the conversion down to 3 clock cycles for unsigned and 4.
I suppose for the class, why is it interesting that it's available to be done in const now? What does const mean?
It means that I can do it in 3 clock cycles or 4 clock cycles on a fixed word, not an array, but on a fixed word, whereas if it wasn't const, it would be more expensive. So in runtime. So that's why I love having this stuff in const.
I was going to say, I think you can also, I know it's maybe mixing a little C++ land in here.
That's okay. It's all related.
Might be mixing a little C++ land in here, but at least the const in C++, and I suspect it's also true for Rust, although I haven't verified it, allows you to lift things out of runtime into compile time.
That's right. That's what we're doing, and that's why it doesn't cost anything at compile time.
Exactly.
It's already been computed.
Speaking of constant, if you want a fun little project that I got myself into, a little task to give myself an excuse to try out AI, I have a friend, he said, I gotta try out Devon AI. And so I was like, okay, I'll try out Devon AI, new AI company. They focus on software engineers. So I had Devon AI look at my open source project. The Rust MSRV for it was kind of old, 1.6 something, 160 something. And I asked Devon AI, what can I constify in this? And amazingly, it actually came back with like 8 good suggestions and then 2 that didn't work out. But anyway, so that's
Nice.
a fun use for both trying out AI and then constifying in Rust.
That's right.
as it
That's very cool.
goes. So,
Yeah, thank you.
did I answer your question?
I was fishing for what is const.
Oh, okay. What is const? It's going to be more complicated than this. I'm going to give you the simplified answer. Const allows you to compute at compile time instead of at runtime. It's more than that. It also allows you to compute at runtime in the case that you can't compute at compile time, but I'm going to just forget about all that for now. So if I have a generic value that might be an 8-bit, it might be a 16-bit, it might be a 32-bit, I don't know what it is while I'm authoring the code, but I need to do bit shifting arithmetic, and that arithmetic would take runtime for me to compute. How many bits do I have? How many bits do I need? What do I have to do? I have to have if-then statements. All of that will be running at runtime, soaking up, performance. If I can push that stuff to compile time, because once I make something generic, the compiler knows how many bits it's going to have, and it does this process called monomorphization. I can actually make all the computations. I can do the bit twiddling at compile time. And then when it runs, there's no computation required. Now, the value that I'm going to operate on won't be known until runtime. But what happens to that value is going to be known, right? How many bits left am I going to shift it? How many bits right am I going to shift it? What am I going to exclusive OR it with? How am I going to cast it? All of the things I might do in order to turn an integer into a fixed point basically can be pre-computed, except for the actual value it's going to receive at runtime. And that gets me right down to the absolute minimum number of clock cycles, which is maximizing my performance. Sorry, I think I misunderstood your question initially. But yeah, that's what it's great for. All right. Oh, one other thing. You've heard me talk about unwrap in production code, right? The hot take, right? The other thing is I love unwrap in production code when it's used with const. Why? Because a panic is a halting of compilation at compile time. And that's a good thing. That's when you get into type state. So you will see me, and I did say there were exceptions, like this is one of them. You will see me use unwrap on a const, because if the arithmetic I'm doing is going to overflow, I'm doing like a checked sub or a checked add or whatever, or overflowing, I will unwrap that or expect that. And then if it panics, instead of actually panicking, it just halts the compilation. And now you know something's wrong. One of your invariants has been violated. So that's another nice thing about doing things at const time. Okay, so tonight's talks, Fast and Safe Image Decoding in Rust by Jonathan. That's going to be intermediate level, 45 minutes. I love imaging. It's near and dear to my heart, so I'm looking forward to that. And I don't know if I'm pronouncing this right. ERE? Is it French?
Extended regular expressions.
Ah, okay. ERE. Compiling regular expressions at build time with proc macros. And that's going to be intermediate advanced, 45 minutes with Kai. All right. So, Jonathan. And I think I have your screens right here.
Actually, I have a slide clicker.
Okay.
Do you have a USB port?
Not an A, I don't. I only have C. Let me see if I have an adapter. Wait, how to make that.
Laptop without a name hidden.
Yeah, I love it. I don't like.
It's almost nostalgic when the floppy drive went away.
I know, right? Here you go. I have one. I do have one. All right. Would you like a lav mic or a hand mic?
Either way. Doesn't like it. All right. So I'm Jonathan. Today I'm going to be talking about creating image decoders in Rust.
I'm not sure you're turned on.
Yeah, it should be green. Okay. So as I'm going, feel free to stop me, ask questions. It's much more fun if it's interactive. If something's confusing, feel free. We can talk about. There'll be code samples. We can. So let's get started. So goals for today. I'm going to give a little bit of background about ImageRS, kind of what it is. Then going to be talking about, first off, what is an image format, and then how do you use them and decode them, and then more on, well, once you are decoding an image, how do you make it fast? So the ImageRS organization, there's this crate on crates.io called Image. It was started actually all the way back in 2014, which actually predates crates.io. The first version is not on crates.io. It was on GitHub, never uploaded to crates.io. I was not around at that time, but I joined later, became the first contributor, then a maintainer. At this point, it's not just the image crate. There's a whole bunch of other crates you can see. There's a crate for PNG, there's a crate for TIFF, for GIF, for WebP files, and a whole bunch more. And just one other thing to highlight, this is made by volunteers. It's not some company's product, it's not corporate funded or anything. This is people volunteering their time, collaborating, and over time, and literally hundreds of people have contributed, building something kind of incredible. So, stepping back, what is an image file? We're going to be talking today about raster image formats, as they're called. In one of these image files, you have a grid of pixels, where each pixel is storing the amount of light associated with that point. So lower numbers, 0, 0, 0 means black. The highest value, frequently these are 8-bit integers, so 255, 255, 255 means white. And there's a lot of complexity that goes into this as far as transforming these three numbers into, every display has slightly different colors, the way things work, so even like this display and what you're seeing are not quite the same. There are ways to represent in image files all of that. We are not going to get into that level of complexity today. And one other detail is that in a lot of image formats, you don't want to store these values uncompressed. They take up tons of space. It would be really wasteful. So we're going to be thinking about how do we compress these values, make them take up less space. So the overall structure of an image format is generally going to have some sort of header that describes overall details of the image. Things like the width, the height. We said frequently they're 8-bit integers. They don't have to be. In the header, it specifies what you're working with. Then you have some pieces of metadata. This is what I was talking about earlier. How do you interpret the colors? But also other kinds of things. Maybe the GPS coordinates of where the picture was taken, the serial number of the camera. There can be some very sensitive things in pictures if you aren't paying attention. So always worthwhile to mention that kind of thing. And then finally, the bulk of the bulk of the file is going to be pixel data. And that's these individual values. Generally,
they're arranged in a specific order, which is the top left pixel is first, then you proceed across right, so the top row of pixels is in that order, and then rows appear consecutively. But different formats do have their own ways of doing it. So now I'm going to talk and focus in a little bit on a specific file format, on PNG. PNG is a fully open format. It's extremely widely used. I'm sure most of you probably are very well familiar with the format. But internally, has a lot of modern features, but is actually way less complicated than you can imagine some other formats are. And another point is that for ImageRS at least, our PNG decoder is both really widely used, slightly horrifyingly widely used, and is extremely performant. It's actually faster than the reference implementation in C, which is kind of surprising. So to look a little bit at how Huffman coding, or how PNG uses compression to store its pixel data, it's this concept of Huffman coding, or Huffman compression. The idea here is that we are going to have a set of symbols. Each symbol is going to be converted into a code word, they're called. And a code word is a series of bits. Common symbols get shorter code words. Rare symbols get longer code words. And by looking at each code word, or even just the sequence of bits that are coming up, you can tell how long the code word is going to be and what it is, and that lets you tell you where the next one might start. So for English text, we have this little example on the slide. The letter Q is pretty rare in English. So if you have a Huffman code to compress English, Q is going to get a long series of bits. And then common letters, vowels, U and E, might be very short codes. So if you were to encode the word Q, which has this first Q that's very long, and then other letters that are much shorter, it'll appear something like this. This is all hypothetical, but kind of gives you an idea of what we're doing what we are doing with a Huffman code. And now, that was a little bit of textual description, but this is a Rust meetup, so let's look at some Rust code. So here, we're actually seeing a full implementation of a Huffman decoder. So it is surprisingly little code required to actually decode this. This is the core loop. There's other pieces, details you'd have to work out for the implementation, but we can actually walk through and kind of see what's going on here. So we see at the start, we have this structure called table entry. And the idea here is that's going to tell us about an individual symbol. So it has what the symbol's value is, and it has how many bits that symbol is. So we're going to have a table of these that we'll look up into. And now we get to the decoding loop. And the first thing we're doing in the decoding loop is we need to read some bits. Since we have a stream of bits, we have to read them. So we have this loop variable that says the number of bits we currently have. If we're less than 12, then we need to read more into our bit buffer. So if you're familiar with bitwise arithmetic, we have this next line that's a little bit complicated. But what it's doing is it is ORing the current value of the bit buffer with a new U32 that we have just read. So we read 4 more bytes of input, and we are going to OR the bit buffer with this 32 additional bits shifted by the number of bits that are currently in the buffer. So can anyone tell me what the result of this will be? Where are the new bits placed in relation to the old bits?
Higher order bits. Most significant bits.
Yes, they'll end up above the bits that are already in the buffer. So what we end up with is 32 more bits, so n bits is incremented by 32, and now we have somewhere between 32 and 43 bits in our buffer, and we can start using that to find out what the next symbol is going to be. So I have this variable table, and it's not actually declared in this code, but what it's doing is we're indexing into table by bit buffer, but we've got this ampersand and then a hexadecimal value. And so what's happening here is that OXFFF is 12 bits of ones. So the lowest 12 bits are all 1. And then the upper bits are all 0. Let's have in hexadecimal, each character is 4 bits, and we have 3 Fs. So the end result is that we have extracted the low 12 bits of our bit buffer, and we indexed into a table. And now, the tricky part I'm not showing on the slide is how do you build a table that will have the values we want. But once you have that table, the actual decoding process just requires you to look with these 12 bits, and it tells you both what symbol did you get and how many of the 12 bits did you use. So you might not use all 12 if the symbol was short, or maybe you do use all 12. But either way, we find out how many bits we've used, shift those off of our bit buffer, decrement our count, and say we've got the symbol. So this is kind of the core decoding loop for Huffman, and as a result, when you're decoding a PNG, this is actually the bulk of the time is a loop like this. Go ahead.
Do you write this in Rust, or is this
Yes.
work doing assembly?
No, this works out actually to be work pretty well in Rust. It compiles down. Go ahead.
I'm a little confused. If your symbol is less than 12 bits, and there's another symbol in your buffer after it, since it's compressed, aren't you doing a table lookup on multiple symbols at once, or what's happening?
Yes, you are.
Okay.
However, you can insert the same symbol at multiple indexes in your table. So every table index so if you had, for instance, a 1-bit symbol, half of your table indexes will be that one symbol.
Gotcha. Okay.
So it appears a whole bunch of times. But this trick means that once you've constructed that table, you don't have to do any fancy branches. You don't have to think, oh, how many bits.
You've given up memory in exchange for speed and size of the thing you're actually.
Exactly. So, yeah, I find this sort of decoding very cool. So once we've got our Huffman code, though, the next thing is, what do these symbols actually mean? And I've been saying symbol. I haven't been saying byte. As you might guess, symbols can be more than just bytes. So our compression is either, if it's less than 255, we treat that is a byte. We've got a new value. If it's more than 255, we have special meanings that we give. So 256 actually says, I want to use different Huffman codes. And so that enables you to have a new block with different Huffman codes. Maybe one part of your image has one pattern, a different part has a different pattern. So that enables some very good improvements in compression if the distribution changes. But then the next thing, and this is what gives you a lot of the compression, is the concept of repetitions. So even higher values indicate that you want to be copying previously seen bytes. So you had some bytes you've already decoded, and then you say, remember those previous bytes? We're going to grab, 3, 4, 200 of them, and we are going to repeat them afterwards again. And so this does not show how you're getting the distance, but you get a length from one Huffman code, and then you actually run a Huffman decoder again, get another symbol, and that symbol says how far back in the stream you should go to start copying bytes. So you have two symbols, and it ends up being this for loop that you can see, where we got a length, we've got a distance, and byte by byte, we copy one after the other. And there's a little bit of optimization that might go into that so that you don't have quite as many dependencies there, but this is the core idea. You're copying byte by byte. And then there's one more big step. Now that we've gotten our individual bytes, we've sort of seen that we want lots of patterns in those bytes, and we want them to be very predictable. The easiest thing to compress is all zeros. If everything is 0, it's great. If almost everything is 0, that also works pretty well. Since our repetition strategy, we can keep repeating that same 0. If you have 100 in a row, it only takes a few symbols to encode. And PNG has a trick on how it can make it more likely that these symbols are 0. And the way it does that is called filtering. What you're trying to do is for each individual pixel, instead of saving the red, green, and blue values, you save a prediction, or you don't save a prediction. You make a prediction, and then save how wrong your prediction was from the value you predicted. So a simple predictor is maybe the previous pixel is a good guess. So you just save how different is the current pixel from the previous one. So if you have an image that's, I don't know, all blue, all the same color blue, you save it in the first pixel. And then the next pixel says, oh, just remember that previous one? And you write 0, 0, 0 for all the differences. And now you've got a way to get all zeros, which you can compress really well. There's some fancier prediction strategies too. I think the ones I've shown are the previous pixel and the pixel above. Those are two of the strategies. A third strategy is you average those two, and so forth. So that was kind of a very quick overview of the basic pieces of PNG decoding. But the other thing is we'd like to make it fast. And so there's a big disclaimer here, which is the way that you make something fast is you benchmark it, identify what's slow, and make that faster. So I should not just be giving you the conclusions from that process. I should be walking you through actually doing the process, but I am going to skip ahead and give a few actual learnings and actual specific optimizations. So the first one is, we actually, on a previous slide, we had this loop. If n bits is less than 12, then do something, otherwise don't. The problem here is that that is very unfriendly to the branch predictor. The CPU, every time it gets to that instruction, has to guess, are you going to take the branch or not? Are you going to need more bits in your bit buffer, or do you already have enough? And the way Huffman works, it's on average, you can guess how many bits per symbol, and so it's maybe every 5 or 6 or whatever it would be, but that's really hard for the CPU because it's just going to keep guessing wrong. It's going to say, oh, every 5, and then it'll be every 6, and so you don't want to have an unpredictable branch like that. We can improve it by having a different strategy for reloading our bit buffer, and then unconditionally saying it's full. So this might require more reading. We have to do more work, but it actually ends up being faster because we're not interfering with the processor's branch prediction.
Question. Is the primary metric, or like the only metric you're really caring about here, is like decoding speed, or are like other things also in consideration that you're going to talk about in like 2 or 3 slides?
So the highest priority is correctness. We get There's absolutely no use in being fast if you're wrong. But provided that it's correct, then I guess our next priority is kind of maintainability. So a slight improvement in speed at the cost of maintainability or at the cost of just being unworkable for future changes would also be rejected. But we do pretty much, once we've factored in like those sorts of factors, it really, we're trying to be as fast as possible. Since that is kind of a big comparison point, is going to be, are you able to match a competing decoder? Are you going to, and one of the weird things that actually happens is that it's not generally one specific image, it's one like number overall. You can say we're 5% slower than this, or we're 10% faster than this other library. Every image exercises different code paths ever so slightly, and can find some adversarial input that like some specific operation, you could be an order of magnitude slower, but only 1 in 1,000 images hits it. And so there's a lot of challenges there too, of how do you identify specific points? How do you deal with trade-offs? One image gets faster, another gets slower. So it's more complicated than just saying that, but
isn't there an instruction you can use where you pre-calculate what the value would be, and then on the instruction it applies it or doesn't?
Yes, conditional move.
Could you repeat the questions, please?
Sure. So the question was, isn't there an instruction you can use that tells you whether or not, or that lets you provide both values and then decide whether or not to use it?
Yeah, avoiding the cache.
Yeah. And so there is an instruction called conditional move. It works out that you don't need it for this operation. And the reason is because you can implement a bit buffer in a way where you're ORing in the same bits again and again. So rather than having a condition on refill, you simply OR the bits in the right place, and those bits will already be set if the bit buffer was full. So it becomes a no-op, but you don't need a conditional move to accomplish it. So then the next optimization, the next point, is around SIMD. And this is one of the pieces that people frequently jump to as, how do you use SIMD to make it all fast? And some parts of decoding you can't use SIMD for. The Huffman decoder that we were seeing, it's sequential. You get one symbol at a time.
What is SIMD?
That is a good thing to say. So SIMD stands for Single Instruction Multiple Data. They are a series of instructions that modern processors have that let you process multiple pieces of data at the same time. Frequently that can be 128 bits, 256 bits, even 512 bits of information. Almost an entire cache line, all at the same time. And so that's operating a much bigger amounts of data than a single U32 or U64 would be. And so that's frequently faster. One of the challenges, though, is that stable Rust doesn't have a safe API for using SIMD. Or this doesn't have a stable API that you can use exclusively with safe code. However, it turns out we can actually get pretty far without actually literally writing any SIMD code, because we can write for loops that the compiler will be very smart, look at and say, I can use SIMD instructions to implement these. So we have an example on the slide that at the top we're individually operating on 1 byte at a time. Each byte depends on something that is bytes per pixel, so a variable amount before the byte you're updating. So that's hard for the compiler to reason about because it doesn't know what this value is going to be ahead of time. Instead, we can, and this comes at a cost, we can individually have different implementations for every possible value that an image file might have. And we know from the PNG spec that there's not very many of them, so it's tolerable. But what this means is when the compiler sees, oh, look, 3 bytes ahead, or 3 bytes previously, all of a sudden, now this is an operation where it can identify that individual consecutive bytes don't depend on each other. So this is kind of a way that we can get a little bit more performance just by guiding the compiler in how it can use SIMD.
Question?
Sure.
Is array bound checking an issue in any of this code?
So that's actually a good point.
The question, please?
Is array bounds checking a problem in any of this code? And so that's one thing that I should probably also mention to make this auto vectorization friendly, is that when you use iterators in Rust, frequently what happens is you say, I want to iterate until we get to the end of this array. And what that means is the compiler can say, well, if you're only iterating till the end of the array, you're never going past the end of the array, so I don't have to do any checks until then. I just figure out how many iterations do I need, and then I can go until then without any bounds checks. So yeah, that's very important to make sure that you're writing code in a way that you aren't getting a bounds check every loop iteration. That would definitely destroy performance. And then one final approach that we would like to use, but actually cannot at the moment, is we'd ideally like to be able to use multiple cores of your computer. A modern processor might have 4 or 8 or 16, tons of CPU cores. They could all independently be running code. But at the moment, we're only able to use one of them for decoding a file. And the reason for that is because these different stages have the dependencies on immediately preceding data. So we don't necessarily know any future point that doesn't depend on previous data. There might be points in the file that are just so different, or maybe even the encoder was friendly and just didn't need to use any previous data. But without some indication of, hey, starting at byte 5000 in the file, you actually don't need anything before it. We don't have any signal out of band to say, how do you find the right point to jump to? So this is something, it's actually, the PNG file format is not set in stone. There's continued standardization work to actually make improvements to the file format. Backwards compatible additions that can improve PNG files that are created going forward. And so there's been ongoing discussion actually about embedding more metadata in the file describing different points that a multi-threaded decoder could jump to that would enable each thread to decode in parallel. So this is something to look out for. So hopefully we'll see that in the future. So let's see, I can wrap up. Just quick overview, as we were saying, image data stores pixels. It's in encoded form. Our job as an image decoder is to reverse the encoding steps that created those pixels. And in PNG, that means we have to do Huffman decompression. We have to expand these repetitions of previously seen bytes. And we have to do an unfiltering pass to recover the actual values of those pixels. So hopefully this convinced you that image codecs are actually kind of fun. And happy to take any other questions if you have them. Thanks. So in what scenarios would this, you say, as an image decoder have a real world effect? Oh, would the speed of an image decoder have a real world effect? Yes. So one case is for a web browser. you're browsing to a different website, and the time it takes to load actually impacts your experience. It impacts how much power your device uses, and it would just be nice if the images loaded faster. And so the amount of processing power that's required depends. Another factor is that maybe your software actually just has a requirement on a particular level of performance, and you're thinking about what library to use. If there's a library in C that's one particular speed, and you're thinking, well, am I okay with using that library? It's got lots of unsafe code. That's very popular writing codecs in C to have tons of unsafe code, tons of assembly. There's been some very critical security vulnerabilities in image codecs, actually, caused by this. But if you're writing an application, you have to decide, well, but can I tolerate the performance loss, potentially, of switching to a codec in a different language? And so if you can match the performance, all of a sudden that concern goes away. And now you can bring safety as a improvement.
So the FFmpeg project, written in C, does video formats. It's wonderful, but it also has the complexity of a whole operating system. Is the project you're on headed in that same direction? And if not, what are you doing to kind of keep control of things?
So I would say that the project started with a...
Sorry to say this, but could you try to summarize
yes,
that?
I will. Yes. So the question is that FFmpeg, as a software product, has tons of C code and has grown extremely large in complexity. Have we been thinking about this as well? And the answer I would give is that the project started with an almost quixotic goal of decoding any image format. And somehow it is held together. We decode a huge number of formats, and actually have pretty strong decoders for many of them. So I think it's a goal to keep going on with that, to keep making improvements. And I think it's the sort of project that will never be finished and will never be complete, but it's still a lot of fun and it's held together.
Yeah, I just have a question about image codecs versus video codecs. Like, I'm old enough to remember motion JPEG, right, where they just stack a bunch of JPEGs together and that's what your camera would give you. Obviously, they're much more advanced today. Is there an intersection? Is there a future, right, where this library moves it also into video, or is there a sister library that has the same aspirations for video?
So the question is that there's also video formats that share a lot of similarity with image formats, and this I would answer that there's actually somewhat of a blurred line. PNG, for example, officially in the very recent spec update, but de facto, actually a long time ago, has an extension called APNG, animated PNG, and that allows you to store multiple frames in the same file. Our library does decode those multiple frames, so we have animation in that way. I don't imagine that the library will go on and support all sorts of video formats, mostly because modern video formats are even more complicated than many of the most complicated image formats. So one of the ways you can make an image format is you look at a video format and you strip out a bunch of stuff and then you package it up. So the AVIF format, for instance, is exactly that. They took AV1 video, they said, you know, we don't need these things about multiple frames, about a frame depends on a previous one, and we have these there's things called deltas, and it's very confusing. We'll strip that out, describe something simpler, that's AV1, or that's AVIF. So our ability to support even AVIF as this very complicated format is more limited. So I don't think that we will go to the point of saying we have a full AV1 codec anytime soon.
You mentioned that there's different filter strategies you could use. Does PNG or any format
like, do they all sort of in the standard, like, hard code the list of strategies you have, or do any of them try to let you, like, put code in the image, you know, but hopefully not kill us all?
So the question is, are the list of filters hard-coded, or can they be extensible in an image? So for most formats, they are hard-coded, but not all. And so JPEG XL actually has this concept of a decision tree that you can embed into the image that is run per pixel to figure out which prediction strategy you use and how you predict the previous pixel. So.
And that's faster?
Oh, it is not faster.
But is it smaller?
But it is smaller, yes. Okay. So that was their goal.
So JPEG XL is smaller.
Yes.
That I would agree with.
So do you think that was a good idea?
I'll reserve judgment on whether that was a good idea. So you had your hand up too.
Yeah. How fragile is the SIMD translations that come from code that's not SIMD? How brittle?
We've had, so the question is how brittle is the auto-vectorization? We've had somewhat mixed results there. We have had regressions at some points, so that has been trade-offs. We actually did also have a regression in some handwritten SIMD code too, in a very bizarre case, but yeah, it is a little bit more tricky than handwriting this, a little bit more tricky to get consistency than handwriting the instructions. But that has trade-offs both ways. It means that as the compiler improves, usually it finds better instruction sequences or better cost models for the processors, and it improves. But occasionally an LLVM update and it can no longer find the same instructions. So it is a trade-off. Yes?
Yes, in the SIMD code, you had the iterator as chunks mute. Is that the key to turning on the SIMD, or is that just something adding in?
So the question is, I was using as chunks mute in the SIMD code, and that actually does help a lot.
Okay.
So yeah, that.
It's like a hint.
Yeah, it's a hint. It basically says I'm breaking this into blocks, and then I'm iterating over the blocks, and that's a signal that the compiler should also operate on those size blocks. And as chunks mute tends to work better than at, let's see, so as arrays, am I saying that right? There's an
array, I was just looking it up, there's an array chunks.
Yeah, so that is much more recent and works better, the as array chunks, I think, versus as chunks, which has been, the as chunks is actually what was more brittle for us. And so switching to a different strategy is how we got back this performance. Let's see.
What's the most complicated format you guys support? Why is it so complicated?
So the question is, what is the most complicated format we support, and why is it so complicated? And so I'm somewhat torn. There's a few of the more complicated ones, and we support them at different levels. So I'd say the most complicated that we have like kind of fully in-house support for is WebP. So this is a file format that has both lossless compression, which is kind of what we were talking about today, also lossy compression, which are basically independent inside the file format. So there's just two pieces, and they say, if you want to decode these files, you have to implement both. And then simultaneously, they also have not just one set of Huffman codes at a time, they have up to, 2 to the 16 different sets of Huffman codes that are used on different blocks. And the different, and also the different channels. So red, green, and blue pixels get different Huffman codes. So you have to alternate between as you're reading the image. They have a larger number of filters. PNG has 4, WebP is like 12 or 13 different. So yeah, they can get more complicated too.
This is a little bit off topic, but are the slides written in types?
So the question is, are the slides written in types? And yes, they are. Types is I think it's actually is written in Rust, if I'm not mistaken. Is a typesetting program that you can use, and I've been wanting to try it. So this was an opportunity to try out actually a Rust program for making slides. So I guess one more question.
When you run your benchmarks, what platforms are you benchmarking on? Are your benchmarks actually running continuously, or is it just on a per performance improvement PR basis?
So the question is, do we have kind of a benchmark platform that we're continuously running them, and kind of which systems are we considering? This is an area that I would love to be more sophisticated in. At the moment, it's kind of on a per PR basis. When you're working on a PR, you run the benchmarks. If it's kind of affecting something that we think might vary, we try to get other contributors to also run it, or other people in the PR thread. You could imagine a lot more sophisticated ways of handling this consistency, since all sorts of things do matter. So, but there's limits to what we have resources for to build and to maintain, and well, just to have. So, all right, thanks everyone.
In a former life, I worked on image formats, and I was part of the team that created JPEG XR, not L, R. And I was actually invited to Lausanne, Switzerland by the JPEG committee, because it was like, ta-da! I think that was the second or third attempt to replace JPEG. It also didn't go anywhere, sadly. And so there's a long history all the way back to JPEG 2000, and everybody's trying to make a better JPEG. And this format just will not die. So JPEG is still king. All right. Thank you for that, Jonathan. Okay, so let's take a 10-minute break. We'll start at 7:20 for the next talk. Okay, thank you.
Go Teams, or does it go through the HDMI?
Yeah, in order for us to be able to record your slides, you know how, can you get onto the Discord?
Yeah, I'm on Discord.
Yeah, I put the link in the Meetup channel there.
Okay.
And then you don't have to install any software. You can just run through your browser.
Okay.
And then Carl will be able to record the slides.
Oh, yeah.
And then your mic, can you use HDMI or do you have USB on the Okay.
Probably don't need that. Well, it was things like, do you need, because I did things like, well, if I just started and, really, you might need something else depending on this, and what they want to do.
If you didn't do that, you would have to run calculations that are the same. And you would use the formula, and you'd be extracting.
Right, yeah, and that's the kind of thing that I would like.
And so, like, you could have questions about that, but if you were a server, it's like, just start coding and explaining.
Yeah,
as I said, if you try one thing, I have a special, like, special surprise in the back.
Yeah, and I always I had one that I used to
You know your example. It's like, oh yeah, we just happen to have a good encoding stations here. And every so often, well, you know that they switch to another table.
Or whatever.
Where that came from. If you do it right, it's really
even have to put up right now. Okay, so if I am, say, calculating, so the hardware gives me an integer from 0 to 4095. That's a 12-bit number. I don't want to work 0 to 4095. I want to work 0.0 to 1.0.
Fixed point.
Fixed point.
I'm familiar with the idea of it.
So it's like floating point, or just think of rational numbers in math.
Yeah, it's just, but it's way simpler than floats.
Way simpler, right? And that's why we're using math. But what I'm doing in this case is standardizing. I don't care whether you're coming in with 12 bits, 14 bits, or 16 bits. The values that you're giving me are some arbitrary range based on the number of bits, but you're always going to get normalized to 0 to 1. 0 is no accelerator, and 1 is max accelerator. Right? 0 is no brake, 1.0 is max brake, right? And in between. So I have to do this conversion for 5 or 6, or maybe 5 different values, 10,000 times a second in the car. So when I look at, let's say, norm, where'd you go, norm? Numeric, norm, there you go. So I want to see. No, I don't want this guy. There we go, okay. So when I define this norm, so here's a case. Now this is very scary looking Rust because it's generic. There's a lot of generics involved. But in this particular case, one of the things I need and you can see the documentation explaining, why I'm doing this, and I'm getting this down to, number of clock cycles. This is like writing assembly language, right, to make it ultra efficient.
Right.
But there's this operation that we don't use very often called exclusive OR.
Yep.
And if I exclusive OR by one value, I can turn a positive value into an unsigned value into a signed value.
Okay.
If I exclusive OR by 0, it will stay unsigned. The compiler will recognize there's nothing to do here, and this line will disappear from the code. So I want, when I'm looking for a signed value, like a steering wheel, -1 to +1, versus an unsigned value, like pedals, going from 0 to 1. This, I don't want to put a branch statement saying if I would need unsigned value, because that causes...
I was just going to say, it sounds like you could avoid a branch.
That's exactly what I'm doing with this.
All right.
So I'm defining choose complement sometimes to be a particular value, and sometimes to be 0. And so how I do that up here is at compile time, as it's called. I'm saying this is going to be some associated type of an associated type.
Yep.
But just think of that as like it's going to be some value based on the generic parameter that gets pushed in.
So where is the formula that uses this constant name choose complement?
Oh, that's what I just showed you. This is the only place it's used.
Oh, I see.
It's this exclusive. Sure. And this is the runtime value. So I don't know what this is at compile time.
Right.
But this gets computed at compile time.
So what you're avoiding is that computation from above just showing up here.
Right.
And in that case, it's kind of a simple one, but you could have something pretty ugly. And I think the constraint is you have to know what the set of things you can pre-compute are versus not.
Exactly right.
Yeah.
And this is actually very limited. You're either going to go from 0 to 1 or -1 to +1. Those are the only two cases. And I only go from -1 to +1 for the steering wheel. So I really know what's going on. So if your generic parameter is this a steering wheel? Or is this an accelerator? I can tell from my generic parameter which case I need. I don't need an if statement at runtime for that. I can look at the generic parameter and say, what's your minimum value? And if the minimum value is 0, I know you're unsigned. If the minimum value is anything other than 0, then I know you're assigned. And that's exactly why I'm using an associated type of an associated type, looking at that minimum value way over here.
I gotta put my glasses on. Okay.
So now I know whether you're unsigned, which is 0, or something else. If you're something else, that minimum value, I don't even know what it is. So you could be an I-16, you could be an I-32, you could be an I-64, you could be an I-side, I don't know what you are. But if that minimum value is less than 0, then this will convert the scale sample into a signed fixed point value. If it is unsigned, this will be 0, and the compiler will erase that line from the code. So I'm like, okay, that's what I need. Right? Cool. Yeah. But I couldn't do that without const. I would actually have an if statement here if I didn't have const.
Right.
Yeah, so that would be really bad.
Thanks.
All right. Hope that helps.
Yeah.
All right. So were you able to share? I can stop sharing if I'm in the cause.
I don't know if I might have to restart my Chrome.
Rest user group. Okay, it looks like I'm not sharing anymore. All right, I'll get out of your way. So you're in the room, right? Sharing your entire screen. Mirroring. There you go. Is this? Yeah, so whatever you're seeing here should be what you're seeing.
Okay. Because currently I'm sharing on Teams as well. But I don't know if that's...
Well, we can find out.
Yeah.
That's confusing.
Oh, you have permissions thing. But will it just work with it plugged in?
Yeah. If we can see it here, then Carl can record. Oh, now I broke it. That's weird. Why is it? It's not. It's giving like a video error. I think that's just Mac not quite doing HDMI. Cool. Leave it. Don't touch it.
Good enough.
All right. Yeah, let's settle in here, and for Kai's presentation, ERE, compiling regular expressions at build time. I have a feeling we're going to see some cons with proc macros.
Maybe a little bit.
Let's see. If it's green, it's
Testing. Cool. All right. Hi everybody. I'm Kai. I'm going to talk about a project I've been working on recently. One of them. It's ERE, stands for Extended Regular Expressions, which you may know if you've used any of the POSIX I guess, regular expressions, utilities. ERE is one of their regular expressions flavors. And the project's about, I guess, compiling those at build time with Proc macros so that you can run them at runtime pre-built. But first, some background. What is a regular expression or a regular language? Formally, a regular language has all these options. You have the empty set, the empty string, symbol, and then you have concatenation of two regular languages, alternation of two regular languages, or a clean star, which means 0 or more repeated of a regular language. And if you've taken a computer science class, you might have seen that. But in the real world, we more see things using these syntactic sugar, where you might have a quantifier, so you have 4 of them, or you have plus, which is 1 or more, question mark is optional, and then these bracket things that are ranges, characters. And so most of the time you're using one of these libraries or another one if you're using another language. For Rust, it's the regex crate by Burnt Sushi, who's did a lot of work. It's really vast, so I've got a lot to catch up on. But the primary way that these run, slide on this, yeah, is that at hello.
Yeah, that interference, I think, is radio interference coming from something that broadcasts periodically. I don't think it's anything you're doing.
Okay.
There's some meetup of radios going on
This is police office headquarters, so yeah.
Okay. Anyway, so first thing that these libraries will do, and actually first of all, just for the regular expressions thing, this is the regular expression here. I guess I should show them here. And what this regular expression is doing is it matches first, it finds a open single quote, then it matches all non-single quote characters until it reaches another single quote. So for example, in this text, it'll match quote, Citizen Kane, end quote, and then this \s means any white space, and then plus means at least one or more than white space. So that will skip this white space here, and then it will match a open parentheses, and then 4 digits, and then an end parentheses. So it will extract here, you can see Citizen Kane, 1941, with the quotes, brackets, and everything, parentheses. But the main thing to note here is, first of all, this is compiling at runtime. So when you call regex new, that's not a const function. You couldn't really compile a regular expression at const or with const because there's just a lot of string manipulation and allocation that needs to be done when compiling a regular expression of any complexity. And then normally that isn't really an issue because it should be pretty fast to compile it, and hopefully you're only compiling it once every run. But what it does mean is you have to include the entire regular expression compiler in your binary, which can be quite a bit. Another thing that you might notice here is when it runs captures, that is not on instructions in your binary, that is on a data structure in your binary, which means there's going to be overhead in terms of running a sort of VM-like system over that data structure. It also has a dynamically sized output because obviously at compile time you don't know how big the output is going to be, so you're basically returning I think they have captures object, but it's basically like a vec, which means that you just need to hope that, or you basically need to hope that you don't accidentally try to access a capture group that doesn't exist. And then finally, we don't like this unwrap. It probably doesn't matter because hopefully you tested your regular expressions, but if you didn't, then that unwrap will crash your program, and there's no thing at compile time that will check to make sure the regular expression is valid. And then a bit of background, I actually learned about these while I was working on this project. There's a thing called lexer generators. Most popular known one is RV2C, which is a little executable that will, they also do output to Rust, so also RV2 Rust, that will take these common things in your code and replace it with equivalent regular expression implementation. So instead of doing it at runtime, it does it like while you're in the code, and it'll insert code into your file that will run or be equivalent to the regular expression you specify. But screen changed. Okay. But the downside, of course, with this is it's not very ergonomic because you gotta like run this script and hope that you don't change your regular expression. Anyway, so introducing ERE, which is the library I made. This is a QR code to the GitHub if you want to check it out while I'm talking or anything. But so here we can see a big difference in syntax. First of all, the build at compile time. So this exclamation mark means that this is calling a proc macro. Actually, any macro. It is a proc macro, which means that this is passed into it not as a string, but as a token. It's just like the actual source code. And then it'll parse that string from the source code, and it will build equivalent code to a regular expression that gets inserted there, where the compile regex macro call would be. And the next thing you might notice is that, so it'll call the compile regex code equivalent to the regular expression, but it doesn't need to serialize over data structure. It's instead just instructions directly in the binary. And then also it knows the size of the captures at build time. So here I have it specifying three, so there's three capture groups. There's the implicit one that captures the entire input, or the entire expression, and then that's capture group 0. And then there's capture group 1, which is the name here, and then there's the capture group 2, that is the date. And as you can see, since it's fixed size, we can now do a, I don't actually know what that's called, but the thing where you like let an array and it will unwrap everything. Destructuring, that's what it's called, yeah. So first of all, I guess just stepping back a bit, what are proc macros? So proc macros are basically a feature in Rust that allows you to define a function in a special proc macro crate that will take basically tokens from the source code and replace them with new tokens that are generated based on those tokens. And it can do a whole lot of things. So you can actually run code, access files, even send web requests at build time. But for this one, it doesn't actually have any side effects. It just internally processes stuff. And so, sorry, go ahead.
Could you explain what a token is at a really high level?
Yeah, so when the Rust compiler, or pretty much any compiler, I think, is going through your source code to build it into the program, it's going to go through and find each like individual piece, so maybe a variable name, a keyword, literal, such as a string or a number, and it's going to turn that into a token. And in Rust, I don't know what it does under the hood, but for the what's passed to the macro is essentially a enum value that's like, okay, this is a literal, and then inside the literal it'll say it's a string, or literal string. I don't know if that's the core thing, but anyway, the main libraries that use for this typically are sym, as in syntax, which is a really nice library for handling like parsing of token streams, and then also quote, which allows you to basically write the code that is going to be inserted, and then you have these like little hashtag interpolations that get included as if it were a format string. Yeah, but generally the idea is that returning this compile regex call, it gets replaced with some code that's generated by this function. Anyway, But about the name of the library, I called it ERE because I ended up picking the POSIX extended regular expressions flavor or standard to implement. This is a bit closer to pure regular expressions than, in some ways, than like your JavaScript PCRE standard. Because PCRE standard, and most things implement something related to that. But anyway, extended regular expressions don't have back references, and they also don't have word boundary assertions, which are also not features in the more theoretical version of regular expression, regular languages. But one downside that I did learn was that POSIX defines its own ambiguous submatching standard, which is hard to implement, rather than the more greedy approach of the PCRE kind of standard. And I'm going to talk more about that near the end, but for now just know that I'm just sticking with the greedy one that you probably see in most languages outside of POSIX utilities for now. But I'm going to eventually have to implement that because the name's a promise, and so I gotta go with it. Anyway, but so in terms of actually building the thing, when I started off, I was kind of like, yeah, this is going to be easy. It was not. So this is kind of generally the process that it goes through to, or that I go through to figure out how to build code to, or equivalent code to a regular expression. So first of all, this starting part is pretty similar to a runtime regular expressions library. In that we're going to parse our regular expression. So this one matches US phone numbers, optionally with the +1. And requiring the dashes, I guess. And it'll turn into an ASD. So it's an abstract syntax tree. So for example, this is basically a concatenation of this like parentheses capture group optionally, and then concatenation of 0-9 ranges, so any digit number 3 times, concatenated with a dash, and then the 3 more digits with a dash, and then 4 more digits, and then here at the beginning and end we have the start anchor and the end anchor, which basically tell it that the string should start at the beginning of the English or the tested string, and it should end at the end. So there shouldn't be any extra space at the beginning or end of the string. This should just be the entire string is a phone number. And so I guess it turned into a syntax tree, which basically, it's a tree with all the different components. Yeah, similar to most compiler things. But the main thing I'm getting into is Thompson NFAs. So Thompson NFA is probably the standard way for converting regular expressions from the tree-based format into a kind of state machine. And here we can kind of see the different components. The general idea here is that with an NFA, you, at any given point, are in one or more states, and given the next input, you can move to one or more states from, or 0 more states technically, from each of the states you're already in. So unlike a DFA or any other, I guess, what you normally think of the state, machine, you're going to be moving, you're going to be multiple states at the same time, which is why it's non-deterministic finite automata rather than deterministic finite automata. And these are, NFAs are basically equivalent to regular expressions, which is why we use them, because graphs are nice. But additionally to this, I guess, first of all, just here in this diagram, you can see all the different components with the Thompson NFA that get converted. So any concatenations turn into the first state machine followed by the second state machine, and then any alternations are like first state machine split into the second state machine. First, you enter and then you split into 2 different states. So you have 2 different states active at the same time that each will be run, and then if, or those of them that pass, are going to continue on. And same with question mark, which is optional, star, which is 0 or more, and then plus, which is 1 or more. The main thing is that we are turning this regular expression into some kind of state machine that is, you can imagine it as like a multi-threaded state machine. And additionally, because we aren't doing like pure NFA, we also have these capture groups, right? Which we need to remember where that was. Like, where along the path did we pass through that open parentheses? Or also, where do we pass through the start anchor? Because if we just did regular NFA, you'd like step through, but you might not, like, I guess, NFAs only know where they are currently. They don't have the global knowledge of, okay, we're at the start. So we need to add in special epsilon transitions, which basically means 0 symbol transitions that will consume, or that will basically be assertions that we are at the start or end. And then additionally, with NFAs, they don't have, or they assume that we are matching the entire string, typically. So we need to add in special implicit loops at start and end to represent that we could start anywhere and end anywhere, which is the way that most regular expressions in practice work, rather than the pure regular languages method, which would say we're matching the entire string. But those loops will be excluded if we have the start and end anchor, because then we'll know that we'll never have to loop through anything to reach the start of the string, or start of the match. Anyway, that was not changing. Okay. That was a lot of talking, but it's probably easier if I just show it. So for example, take this expression. So it, first of all, this match needs to start at the start of the string, which we see the this thing that, and then it will capture either A, B, or A, C, and then 1 or more Ds, and then optionally an E. And then since there's no end anchor, it can have any number of characters after it, but those will not be included in the match. And so this is actually the original thing that we get out of the original NFA that we get out of the Thompson NFA construction, but that's really complicated, so we optimize it down into this. And as you can see, we start at the beginning, and then we're going to, did I draw? No, okay. Let's skip to this one. So we're going to start at the beginning, and, ooh, this is slow. Let's wait for it. There we go. We're going to start at the beginning. We're at the start state, and the point we are at the input, actually this is one of the engines that I have, is flat, lockstep, NFA. So the reason it's flat is that all epsilon transitions occur at once, and the reason it's lockstep is that all threads are always at the same point in the input. But I'll just show that on the diagram, I guess. So we start, sorry, do you have a raising hand?
Oh, no, just scratching my eyebrows.
So first we're going to do the epsilon transitions. So that is going to go to, ooh, this is slow. I guess, so we're going to go past the first open parentheses, which is kind of implicit, it's not actually shown in this, but the 0 capture group always includes the entire match. And then we're going to have the assertion that we're at the beginning of the string. If we weren't at the beginning of the string, right, where you have the beginning of the string here, then it would not continue on, and in which case it would reject because there would be no active states. Then we're going to pass through here, which will set the 1, which is this, the first capture group open bracket, or parentheses. And then here we have 2 paths we're going to go on, which means we'll have 2 active threads. And as you can see here, if you look closely, this one is epsilon 0, and this one is epsilon 1, which signify the priorities. Because if we ended up in finishing with 2 active threads, we want to know which one to take the capture groups from. But so we end up here at the first epsilon transition. We haven't consumed any symbols yet. Then we take 1 symbol transition, so in this case it's an A, which both of them actually start with A. So both of them will continue on, fake symbols. Then an epsilon transition again, which actually won't move because there are no like epsilon transitions to go through. We're just already at it. So the next one is a symbol transition. Once it goes, we consumed a C, which means that the top thread up here didn't continue on because it doesn't have a C to consume, it takes a B, but the bottom thread continues. And then again, with the epsilon transition, we're going to pass through the end of the capture group index 1, once this goes, there we go, which means that that will be added to the thread, so that we now know that, and those are all recording the indices at which we pass through them, which means that we know that the beginning of capture group 0 and 1 occur at index 0, and the end of capture group 1 occur at index 2. Yeah. And then I guess we're going to do another symbol transition. We're going to go through the D here, which is required 1 at least by their expression. And then we're going to do the epsilon transition, which is going to give us a going to give us a huge number of states. And as you can see, they all have their own priorities. So with epsilon 0, we go here first, which has the lowest or highest priority. Then we're going to go through the epsilon 1, which is going to give the next priority. Then we're actually going to go through epsilon 2, which is going to go further propagated to the second priority, which is actually the accept state. But since we're not at the end of the string, we're not going to do the accept. And we're also going to end up here, which is lower priority since propagating out from state 14, we go through the higher priority epsilon 0 out of state 14 first, which means that state 13 has the lowest priority. And all of these threads will have the same capture group field set except for thread 2 since it passed, threads 2 and 3 since they passed through the end of capture group 0. But anyway, long story short, only 2 states will survive going through the next D symbol transition. This one actually matches D, and then this one is the end loop that will match any character. So this is basically an empty negated set, which means it will end up here at Q14. And then we're going to keep doing that on and on. But I'm not going to make you sit through that because this is slow. But anyway, it's going to end up with this kind of match statement of which state it's in and what the next character is in. But you know, that's operating over characters, which are a bit of overhead to decode every single character and match. It'd be much faster if we could just do this over U8s. So instead of decoding chars into between 1 and 4 bytes for UTF-8 code points, we could do every single byte and just decompose every character range into the individual ranges of U8s that we could have. So here's actually the full, this chart is the full process for matching any one Unicode or UTF-8 code point. It's pretty complicated, and so I'm glad I don't have to write that myself. But I guess the code I wrote will convert from chars into UTF-8, which will add a large number of states if you're not using only ASCII in your regular expression. And that also includes if you have like negated sets, because if you say anything's not an A, that includes all of the UTF-8 code points that aren't an A, which is like a lot of them. But anyway, we're splitting multi-byte characters into multiple states so that we can go through each byte in that appropriately. We're going to combine similar sequences with same kind of optimizations we did with the character-based TNFA. And then there's various other optimizations that I do, not going to go into details on that. Switch. And so there's a similar engine to the flat lockstep NFA for chars that's for U8s here. It basically is going to be faster because you don't have to have the overhead of decoding chars, but it will be larger because there's going to be more states since there's more bytes and more paths through each code point, basically, to like up to 4 different states for a single char, just because you have to handle with the 4 different bytes. And so, yeah. But the main thing here is that that will be included in the binary size, since all of this is getting compiled into the binary rather than just being a string that gets compiled at runtime. Anyway. Oh, I should go fast. Okay, so another engine I have, basically, I'm sorry, step back. The ERE will, depending on the properties of the regular expression that's passed in, it can select one of these engines that it thinks will be the most efficient, or best fitting, or whatever you want to optimize for. Currently it's just fastest. But in this case, one-pass regular expressions are a subset of regular expressions where there's no more than one single transition at each step. So before we had that case where it branched out and then there were 2 transitions at the same time that both matched an A, that would not be one-pass regular expression. And so you can also think of it as the cases where the power set DFA only has states representing one NFA state. We're talking more about DFAs in a bit. If I don't know. Yes. No wait. It's okay. Whatever. But the important benefit here is that we're going through the NFA, but only ever have one thread at most, which means we don't have to handle duplicate threads or thread priorities. We're just going to do one at a time, which is faster. So for example, this one, cell4, is not one pass. As I said, here, the A's, they will both match at the start of the string, which means that we will have 2 different threads active at the same time. And then again, here, if you are at state 10, for example, then you're going to go through epsilon and then back through D. Then if you're also at state 10, then you can go through all these epsilons which don't consume anything. And you're going to match this, which will also match a D because it matches everything.
I have a question.
Yeah, go ahead.
When you say threads, are you saying conceptual threads, or does that also mean like you implemented it, it's creating like a process thread?
No, these are conceptual threads. So it's basically for the NFA or flat lockstep NFA engines, it's a basically a vec of like a stack of enum states that.
So it's single threaded is how it's.
Yeah. Because I think there'd be so much overhead just to start up threads for text matching, unless you were going through a massive document. But anyway, so the next one, this one, actually wait, it was really slow. Okay, this regular expression is one pass, and it looks complicated, but really what it does is it matches numbers optionally with a decimal point in the middle. But really, the reason it's one pass is that we are split across this dot. Meaning that we're going to be matching, sorry, no, this isn't the same one. This one is domain names. So it matches, it's not perfect, regular sort of domain names, but it matches dashes and then alphanumeric, and then it has one or more sets with a dot and then another domain segment. But since it's separated always by dots, it always knows whether it's continuing the current domain segment, or if it's transferring to this next one, which means that there's never any point where there's ambiguity in which thread we're going through, which means that we never will need more than one thread, and there's a lot of optimizations to do off of that. We'll see. Ooh. All right. There are two separate kind of implementations that this turns into. The first one is the match-based implementation. So in this one, first of all, the state at the top is not a vec in this one because there's only ever one state at most. But we're basically just going to match what the current state is and what the next character is. And optionally, this if I equals 0 just means if we're passing through a start anchor to assert that we are at the start, then that's an additional condition. It'll just set the next state, which this one's actually really fast, especially because we get the benefit of being compiled. You can get through a lot. The problem is it would be faster if we could immediately jump to the next thing instead of having to check in the next loop which match condition or match case or act. So the other implementation is a function-based implementation, which has basically state 0 and then it only matches on the next byte rather than having to match on what the current state is, which means that we can always jump to the next state. So, for example, here we are calling func state 4, which will then run whatever conditions we need to check for when we're at state 4. And this also means that we can potentially have states that check multiple bytes. For example, if we have a sequence that never diverges, so let's say for let's say we just want to match a static string as part of it. We want to match red, let's say, inside of a larger expression. When we get to that state, it'll just match the entire sequence red instead of having to call for each byte, which is another advantage of this function-based implementation. The downside is that until the become keyword is standardized, it has potentially unbounded stack growth if the compiler doesn't decide to include tail call optimization, which is why for most cases the library will prefer the match-based implementation even if it's slightly slower. And then finally, how much time do I have?
We can run until about 8:10.
Okay, I'm gonna go fast.
That wasn't fast.
I might have over-prepared. I don't know. Anyway, so lastly, we're going to be converting the last intermediate state is the TDFA, which is a system where instead of having multiple threads, we basically combine all the combinations of possible threads into a state, which is the power set DFA construction. Notably, since we have these tags with different priority orders, in addition, unlike a normal DFA, we're going to have, or a normal power set DFA, we're going to have individual states based on the priority. So if we have a state that represents state 1 in the NFA and then state 2 in the NFA, and then we have another one that has 2 as higher priority than 1, those are going to have to be separate DFA states rather than having it be set-based. And then also the power set conversion for NFAs to DFAs is worst case exponential size, which means that we have to bound it, which means that not all cases can become DFAs, even though they're faster, since you don't have to manage multiple threads similar to the one pass. It just potentially is a lot more states. So here's an example. I guess this is the NFA at the top, and this is the DFA. The additional metadata basically with these capture groups and anchors is included here. I just didn't include in the diagram. But it's going to, instead of having all these epsilon transitions that we're going around, we're just immediately on the next transition matching some character and then including the capture group tags in that data. And so this means that we're basically doing one transition at every byte and ending up in one state at every byte rather than having multiple states at the same time, which can get messy. Although, again, it could have potentially much higher DFA size, more states, since, for example, in this one, we have one state that represents both 3 and 6, rather than individual states just having it represented separately. Yeah, the main thing here is that each of the DFA states represents the tags for all its individual NFA states within. So, for example, 3 and 6 would have 2 fields. Let's say 2. Where I represent this is the state will have this old tags field, which is an array with the size of the number of NFA states it represents. And then for each of inside of that array is another subarray that is for each of the capture groups that it has, which means we're basically tracking all the same data you would be tracking with the NFA, just inside of an individual DFA state to remember where all the capture group beginning and ends are. And then there's one last engine that is kind of a meta engine. That runs test on cases where the capture groups are fixed offsets into the matched text. And so it runs tests on it, which is just a Boolean of whether it matches or not, and then it can afterwards index it, which means you don't have to maintain the indices of where all the threads match their texts all the way through. We just say it is a match or not, and then index in and grab out strings. Right, what's next? First of all, the POSIX ambiguous submatching is something you have to still do. With this example here, the current greedy approach will prefer, so with this ABCD, it will prefer to first grab the A for this capture group. So we get A, not the AB, because A is earlier in the alternation. And so it'll pick A, and then the B will end up at this question mark. And similarly here, we will end up with AB and then B, because we have 2 Bs, which means that the only possible match is the AB here, rather than this case where it could be A and then B, or it could be AB and then no B. But also separately, with the POSIX standard, once this loads, it says that for these alternations, and there's various other things that it says, but this is one of the big ones, is that it should pick the biggest option, like the longest one. So it's going to pick AB always, which is it turns out, there's no linear time way to implement this that is known. Obviously, this doesn't actually matter for test, because we don't care about capturing which submatch we capture. We're just going to say this is or is not. So there's an equivalent in that case. And then one-pass equivalents also never have ambiguous submatching, which is what kind of defines them, as they never are going to be multiple threads at once. But yeah, the POSIX standard is easier to describe, but harder to implement and less efficient. So that's something I'm still working on. Another thing I'm still working on is with the become, I mentioned earlier, become keyword stabilization. It essentially can allow these functions to act like go-tos to each other, instead of having to either rematch every loop, or rematch the current state every loop, or have without, or depending on what the compiler decides to do, could have unbounded stack growth. And then finally, the current way I'm defining regular expressions, or the current usage, I guess, method, is that you have this object, the regex object, with some constant generic of the number of capture groups it has. But the problem here is that it's always going to have this option that says we might or might not have a year, right? But we know from this regular expression at compile time, which is when it's compiling, that any match is always going to have a year, because that's how the structure of the regular expression is. Which means that really we don't need that option there. We could have for example, a struct, as this loads, that says This one matches an RGBA value, optionally with the alpha. We could say that the entire match will always exist. Or if there's a match, the R will always exist if the red will always exist if there's a match. The blue will always exist if there's a match. The green will always exist if there's a match. But the alpha may or may not exist if there's a match. And this is actually implemented currently. It's had a feature flag because I haven't decided on the actual interface yet. But this allows for a lot more like static definition and reduction of unwraps potentially that kind of scraps that itch. Yeah. Oh, also, I think there's in some slides, but I'll skip over it. With the regex struct, it basically is just a struct that contains two function pointers. Whereas with this strategy, we could directly implement them as like an input block on the struct that we're adding it onto, or as a derived helper for a trait. Optionally, I haven't decided on the exact semantics of how I'm going to do that. Anyway, does anybody have any questions? This is the GitHub project, and then I'm also looking for a job. If anybody knows, so that's my LinkedIn. You can talk to me after.
I have two questions. I haven't seen this before. I've been looking for a compile time regular expression crate for a long time. I didn't even know this existed. I've been looking for one, so this is awesome. And you should definitely, there's like 2 issues on the Rust regex crate where Burnt Sushi said, I can't do this, it's too hard. This is really impressive because Burnt Sushi said, I can't do this.
Well, so when I was really making this, I think I saw some of those things. And I don't think they said it was, yeah, they said that you said that you've been looking through, or for, I guess, a compile time regular expressions library, and mentioned that Burnt Sushi on the like actual regex crate had said that they weren't going to be able to build a compile time version. I don't think it was that it's too hard necessarily. There are some complexities, but I think the main thing that they said on those different threads was that, and I did mention, one of the downsides of this is that you actually can't compile at runtime because everything is proc macros. So being able to have that be compatible with the existing Rust or regex crate would be nearly impossible, which is why they were ruling that out for the regex crate. Go ahead. Yeah. I guess, do you want a microphone? It might be easier.
Is this working? Yeah. I guess my next question is, have you done, what would be really fun is just to see like runtime comparisons of your crate running. Because I know from the project, my little open source project that I've been working on, that one of the big savings you get is the regex compile time. So that upfront cost is now just at compile time. So it'd be really fun. I don't know if you have on your crate website, but it'd be fun to have like little table comparisons of how yours.
Yeah, so I mean that's hard. I've been currently open for on my laptop, but what I've found so far is that my library is faster in cases that are like anchored, and then it's like where the match is the entire input string, but it's slower in cases where you are searching through a large haystack for some text. And that's probably just I haven't implemented good strategies for implementing or searching in haystacks, because I'm primarily focused on the short match case. But yeah, it's always more to do.
Are there any opportunities where you can do like really expensive tests? Sure. Like, is it possible or practical to do something really dumb and expensive? Like, I don't know, just like try the regex on 100 different engines and see which one's faster, and then pick that one because it's compile time and get away with it. Like, have you done anything like that?
There. So I kind of thought about that, and the main issue there, I think, is that like you could probably add like a macro attribute that's just like when you're compiling this, spend as much time as you like. But the time it takes really depends on the input you're giving to the regular expression, which means that you have to also specify a list of example inputs, which means that the attribute definition would get several lines long. So you probably could, but it's also, at least with the current engines I have, pretty clear cut. There's a hierarchy of the lockstep ones are the slowest, but they're the most general case, and then the one pass and fixed offset are the fastest, but very limited cases. Actually, one pass, most real world cases, if you have start and end anchors, probably match the one pass case, but obviously you can't just only support that, so we've got the other cases as well. But yeah, the hierarchy definitely means that currently, and this will possibly change as we get more engines, but currently it's pretty clear cut which one's fastest.
It seemed to me like you were paying attention to making it look nice for the user. What was your design process for that? Did you do you have sample code using regular expressions in your kind of writing documentation even before people are reading it? What are your thoughts on that?
I mean, I don't know. I kind of put it in this is what I would want to use. I don't know. The main idea was it should tell you everything up at front at compile time, and after that it should just be functions you call. But beyond that, I mean, there's documentation on the Cresa.io page. But yeah, a lot of it just came out of once you have functions to call, what's the most convenient method to call them, and that's it. Actually, with the current way with the regex struct is probably actually not super convenient because you have to define this whole ooh, let's get back. You have to be define const something, which potentially can cause copying. Well, I don't know why you would. I guess they're just function pointers, but recompilation maybe. And it also, I don't know. I don't think it's very nice currently, but the hopefully future struct or even enum possibly, you could have this set of cap attributes could be matched, or this set of cap attributes could be matched, and internally you could possibly figure out that it is an exhaustive set of which cap attributes could be matched. That's my other idea, but that probably be a little more complicated to do visually.
It's good to be thinking about things that turn into something nice to read and write.
Yeah, it's the main idea here is making regular expressions fit nicely into the Rust type system, which seems to have come with some of the benefits. Anybody else? Guess we do have to go.
Well, I'm going to second. I think someone said that was incredibly impressive work, so I think it's very impressive.